Hi, my name is Nora Hofer and I'm a PhD student at the University of Innsbruck in the Austrian Alps. Recently, I had the opportunity to present my work at the Information Hiding and Multimedia Security Workshop in Chicago. The title of my paper is Progressive JPEGs in the Wild, and here I want to share with you what I find exciting about it. Let's start. In its baseline mode, a JPEG image is displayed sequentially from top to bottom. In the so-called progressive mode, an image is displayed at a low quality first and details are added progressively. This mode is useful whenever images are transmitted over a slow communication link, for example, if your smartphone has bad reception. Let's have a closer look at how this is done. Sequential and progressive mode differ in the order in which the data is stored in an image. This can be displayed with this cube. On the vertical axis, we see 64 subbands of quantized DCT coefficients in zigzag order. On the horizontal axis, we have the precision of the coefficient values from the most to the least significant bit. On the third axis, we have all blocks contained in the image. In progressive mode, the image data is partitioned into multiple scans. How exactly is specified in a so-called scan script. Let's look at this example scan script containing 6 scans. In this case, the initial scan 1 contains the DC coefficient without the least significant bit. Decoding this scan alone results in an image showing the average color per block. Scan 2 contains the first 2 low frequency AC coefficient subbands without the 3 LSBs. Scan 3 contains also the high frequency coefficients, again without the 3 lowest bits. You probably get the idea already. After all scans are received, the transmitted information is the same as if it had been sent sequentially. The progressive mode exists since the first version of the standard from 1992. But is it actually used? To answer this question, we collected 200,000 images sampled from historical JPEGs on the 5,000 most visited websites between 2005 and today. Surprisingly, nowadays every third image is progressive. We also Googled and found developer blog posts from Yelp, Instagram, Twitter and Facebook writing why they adopt the progressive mode. Looking at the plot again, we can see an increased share of progressive JPEGs after 2014. This is the year when MOSJPEG was introduced. MOSJPEG is an open source JPEG compression library designed for web publishers. Its goal is to increase user experience by reducing web page loading times. Recall that also libJPEG, the de facto reference implementation of the JPEG standard, does support progressive mode. For example, this image gets compressed to a slightly smaller file size when instructing libJPEG to use progressive mode. Now, if we compress the same image using MOSJPEG, which uses progressive mode by default, we can reduce the file size even further. However, this does not come for free. What you can see here in red are pixel blocks, which differ in at least one DCT coefficient between libJPEG and MOSJPEG. This is surprising. Apparently MOSJPEG does more to the image data than just reorganizing it in scans. In fact, it introduces a novel way to optimize the rate distortion trade-off. We see our contribution to the field in a better understanding of the implications. We identified the origin of these differences and discuss how this may affect steganography, steganalysis, and digital image forensics. Let's see how. This diagram visualizes the baseline JPEG compression pipeline. We start with image processing, apply DCT, quantize and produce a bit stream by applying run length and Huffman encoding before we store the data to a file. Now we add MOSJPEG's modification to the diagram. Here is the novel rate distortion optimization, which is inspired by trellis quantization. Moreover, as most JPEG uses progressive by default, it selects scan scripts based on the image content. Let's look into trellis quantization. Assume we have this size distortion space. Most JPEG tries to change the quantized TCT coefficients in a way to move each block to the left on the size axis while staying as low as possible on the distortion axis. This is done by the optimization of this cost function, which accounts for the size in bits needed to encode a coefficient plus the distortion that is introduced by the quantization. Let's look at the size. Assume we want to encode the following sequence of quantized TCT coefficients 3, 0, 0, 8, 0, 4. There are two things to keep in mind while generating the bit stream. First, only non-zero coefficients plus the number of preceding zeros are encoded. In our example, we will encode the 3, the 8 plus 2 preceding zeros, and the 4 plus 1 preceding zero. The second thing to keep in mind is that the non-zero coefficient itself is actually not subject to Huffman encoding. Looking at the stream, we can see that 3, 8 and 4 are represented with variable length. The actual length in bits, as well as the number of preceding zeros, is stored in control bytes, which are Huffman encoded. To compose the control bytes, we can use the table on the right. Rows represent the number of preceding zeros, and columns represent the number of bits needed to store the coefficient value. Look at the example of 008. Here we have 2 zeros and need 4 bits to store the value 8. That means we can take our Huffman table and use the symbol at index 36. Following this pattern, the whole sequence is encoded by alternating Huffman control bytes and variable length coefficient values. In our case, we need 29 bits to store it. Trellis quantization now tries to reduce the size. To do so, it uses the table on the left, that we will call size tree from now on. This tree contains coefficient values grouped in rows by the number of bits needed to represent them. Trellis quantization calculates the total bits it could save if it replaced a non-zero coefficient with the highest value of every lower size group. For example, for the coefficient 8, the alternative candidates are 7, 3, and 1. Now, if we change the 8 to a 7, we use the symbol at index 35 and can save 2 bits in total, 1 for the coefficient value and 1 for the control byte. Trellis quantization also tries to increase the length of zero runs. Changing the 3 in our example sequence to a 0 would allow us to save another 4 bits. Of course, we cannot do this arbitrarily without destroying the image. For these changes to remain unnoticeable, the distortion needs to be considered. The distortion is based on the square error between the unquantized coefficient y sub I and the dequantized coefficient. Q sub I is the quantization factor in subband I. The distortion is then multiplied by lambda sub I, defined in most JPEG's perceptual model. This model is a variant of PSNR HVS, where HVS means that the metric is adapted to the human visual system. If you want to learn more about it, you can look up these 2 papers. A big advantage of the model is that it is additive in the DCT domain. No transformation to the spatial domain is needed. The lambda is scaled to the size in bits, so that it can be used to calculate the cost. The last sum of this term adds the distortion of the preceding zero run. Now, let's see how that would look like for an example. Assume this sequence of AC coefficients. Now we want to perform the trellis quantization to optimize the coefficient at index 4. The unquantized coefficient value is 540. It gets divided by the quantization factor 72 and rounded to the nearest integer, 8. Like before, we use the size tree to get these alternative candidates of shorter encodings. Again, those are 7, 3 and 1. For the sake of space, we will only look at 7 for now. We start with calculating the size. As before, we can save 2 bits. Next, we calculate the distortion that we introduced by this optimization. We therefore evaluate the equation. In this case, the distortion is the same for both candidates. This is because the quantization error is exactly half of the quantization factor. That means we are able to move leftwards in the size distortion space without going upwards. For completeness, let's see the case of the other 2 candidates. Well, okay, here the distortion gets too high, let's not do that. Internally, MustJPEG performs all these comparisons and backtracks to the best solution found. Now, as we know how MustJPEG works, let's discuss how it affects our fields of interest. We start with steganography and steg analysis. What you can see here is the histogram of the first AC coefficient subband of 100 grayscale images. As expected for natural images, it is approximately Laplace distributed. If we compress the same images using MustJPEG, the histogram changes. The trellis quantization shifts the distortion towards 0 and amplifies the coefficients of absolute value 1, 3, 7, 15, 31, and so on. Recall that these are the candidate coefficients which take the maximum value of the next shorter variable length encoding. As these coefficients occur more frequently, outer neighboring coefficients occur less often. We conjecture that this has implications for steganography. On the one hand, these artifacts resemble the changes introduced by no steganographic embedding functions. This means that detectors which are unaware of MustJPEG might wrongly classify these images as positives. On the other hand, steganographers could try to mimic MustJPEG artifacts in an attempt to remain undetected. Finally, let us turn to digital image forensics. I have mentioned that MustJPEG implements scan script optimization. This procedure searches through about 1,000 different scan script variants to compose the script which produces the shortest output size. Unlike trellis quantization, this optimization does not alter the signal. In an experiment, we extracted the scan scripts of images from the Folkheim dataset. The dataset includes 23,000 images that are sent via different social media platforms, 97% of which are in a progressive mode. Note that color images in fact use 3 scripts, 1 for each channel. To our surprise, we found only 3 different scan scripts in the whole dataset, and we were able to link the extracted scripts to the social media platform the image was sent over. All images originating from Facebook, Telegram, and Twitter use one default scan script. WhatsApp and Instagram, however, use specific distinct scan scripts for all images. That means we can potentially use the scan script as a trace for platform identification. Additionally, if we find a scan script that is optimal for the image content, it might indicate that MustJPEG was used for compression. Now, to conclude, I want to emphasize that the MustJPEG compression library calls into question the reliability of established methods in steganography, steganalysis, and image forensics. The community should incorporate this knowledge about MustJPEG into future research to improve the reliability of its methods. Thank you very much for watching. If you want to learn more, please check out my homepage to find the paper as well as other research works.